Hello everyone, welcome to class 19. So today we will continue our discussion on point groups, and so until last class we have been looking at various crystal systems and the different point groups that are developed from looking at the symmetry operations in various crystal systems. We were in fact we stopped at a point where we said cubic system, so if you have to really understand the point groups of cubic system, one needs to look at the stereograms, and using the stereograms you can understand what are the different point symmetry operations about what axes, and all these are grouped together in the form of a point group, which is very well compactly represented in the form of a stereographic projection, right. So we said a cubic system should have so at least the minimum requirement for a cubic system is it should have 4 3-fold axes of symmetry about the 1 1 1 axes. All the 1 1 1 axes are 3-fold axis of symmetry. And so we said if that is the case, so a 2-fold axis about the principal axis, which is ABC, comes for free. So the minimum point group symmetry that we have in a cubic system is 2 3, right. However, so you can also have cubic systems, or if I have 4 3 bar axis of symmetry, that is also cubic. Then what ensues is our mirror planes, right. So mirror planes which are parallel to the major axis, the principal axis ABC, right. So that is the M3 bar point group. So we said in a cubic system we can have 2 3, we can have M3 bar. These are the point groups where there is no 4-fold axis. So these point groups actually quell our misnotions that so if I have a material with cubic symmetry, it should have 4-fold axis, it should have at least 3 4-fold axis of symmetry, right. So 3 orthogonal 4-fold axis of symmetry, that is wrong, right. So it is not necessary. A cubic system should have 4 3-fold axis of symmetry, and the point groups 2 3 and M3 bar, which are which are point groups of a cubic system, they do not have 4-fold axis of symmetry. And one of the examples we were looking at is cristobalite, right, whose underlying point group is 2 3, right. So from space group, we will look at space groups in the next class. Very briefly we will touch upon what space groups are, but from every space group you can see what the underlying point group of that crystal is, and the underlying point group determines the properties of crystal, and here the underlying point group is 2 3, right. So in 2 3 we understand that this is a cubic system. However, there is no 4-fold axis of symmetry, that we saw by visualizing it, okay. Now today we will and then we said if there is a 4-fold axis of symmetry, right, if there is one 4-fold axis of symmetry, it turns out that you should have 3 4-fold axis of symmetry by virtue of having 3-fold axes, so 4 3-fold axes. And so if so the point group such as 4 3 2, right, means so I think we can look at the stereogram and understand what this is. Yeah. So here we were looking at this, let me point out with a pointer. So we were looking at this particular thing, right. This is 4 3 2, and 4 3 2 we have 3 4-fold axes, right. So 0 0 1, 0 1 0 and 1 0 0, all of them are 4-fold axes. But then all the diagonals, the 1 1 1 0 set of directions all become 2-fold axis of symmetry, and of course we have 1 1 1s, 4 1 1 1s, which are the 3-fold axis of symmetry. So you have all these elements that are present in a 4 3 2 sort of point group, right. So if I count the number of elements in this point group, right, so the number of elements starts increasing from 2 3, and then the the holohedral point group of the cubic system is M3 bar M, or 4 by M 3 bar 2 by M. and that is so there we also pointed out where the M3 bar M point is it's in an it's sitting in an octahedral void in an FCC metal such as platinum, for example. We pointed out that I have an octahedron formed by two triangles which are pointing which are rotated by 180 degrees with respect to each other, and there is a void in between. That void is the point about which I have an M3 bar M symmetry, right. So that is a point group. So all these operations can be operated about that point. That is a very high symmetry point in an FCC metal. Okay. So we gave you examples, and then so if you look at the total number of point group operation symmetry operations, they are 48, right. So this is the holohedral group, and the number of operations just keep increasing, right. So as the symmetry keeps increasing. So that is the thing about cubic systems, right. So today we will start by actually looking at one more example. So let me open Vesta of zinc sulfide. So I asked you to actually look at let me open Vesta. So we ended last class by saying that you can actually download all these structures, what are so called CIF files, CIF meaning crystallography information files. They are available in materials databases, right. So materials project database being one, the so these are freely available essentially, the crystallography open database, right. So all these things you can just download the structures and then try to visualize it yourself, right. So using a software such as Vesta. So zinc sulfide, I have done that. So I have downloaded it here in my folder, put it in my folder, and here it is. So what I am coloring here, all the tetrahedra, right. So you can see that all the tetrahedra. So this is perhaps yes. So I hope you can see my pointer. So zinc atom is this grayish atom, and this grayish atom is surrounded by, I can visualize it, right. So I can rotate it around. It is surrounded by 4 1 2 3 and 4, right. So the coordination number of this grayish atom is 4. Okay. So it is forming a tetrahedron. I can see that there is a tetrahedron that is formed here. Okay. Now if I so like I did in my hypothetical example, all these tetrahedra are arranged nicely with respect to each other, right. So next to one tetrahedron the second tetrahedron is placed, next to that the third tetrahedron is placed, and so on and so forth, right. So you see as I have shown you, right. So earlier I was just drawing tetrahedra and saying that why don't you arrange them nicely, and so in this case so I said this is one axis, so these are sulfur atoms which are on the top, these are sulfur atoms which are on the bottom, right, and in between is my zinc atom, that is your tetrahedron, and you keep on arranging the same things in the same sequence, right. So very nicely you arrange all these zinc sulfur atoms on the bottom in the same line, and zinc the pink sulfur atoms on the top in this orientation, right, and then zinc is in the middle, right. So this is a more symmetric structure, right. So I am arranging so that I do not lose out, I am arranging all these tetrahedra next to each other so that I do not lose out on the fundamental symmetry that an isolated tetrahedron has, which is a 4 bar symmetry, right. Whereas in case of cristobalite, I have arranged it in such a way that I could preserve the 3-fold axis of symmetry, but not the 4-fold axis of symmetry, right. So or the 4 bar axis of symmetry, the 4 bar point symmetry operation. So what you get here in zinc sulfide is hence so you will have 4 bar, right. So 4 bar is not lost, and so of course it is a cubic system. So you will also have, if you are watching the zinc sulfide, right. So you can see that so if I watch it along the A axis, right, and then rotate it 90 degrees, nothing really changes. Rotate it again, I mean, so the by 180 degrees nothing really changes, and so on and so forth, right. So I mean, so these lines seem to be changing, but I mean, so the atomic positions, if you look at the atomic positions, nothing is really changing. Just by rotating by 90 degrees, in whichever direction, nothing is changing, right. So there is a 4-fold axis of symmetry here. There is a 4 bar symmetry, right. So the lines change a bit, but you can prove to yourself that the tetrahedral 4 bar symmetry is retained in this crystal. Okay. And of course, if I orient this crystal about, let us say 1 1 1, I am going to the projection vector, which is 1 1 1, and the upward vector. Projection vector means I am actually viewing the crystal about 1 1 1. The vector that comes out of the plane of this board is the 1 1 1 vector, and the vector that points to the top of this page, right. So vertically up, that is the 1 1 0, or that is something 1 1 bar 0, which is perpendicular to the 1 1 1 direction. Okay. So I can visualize it this way, and when I am visualizing it this way, so I can rotate it by 120 degrees, nothing really happened, right. So I am rotating it by 120 degrees, nothing is happening, right. Whereas in case if I watch it along a axis and rotate it by 90 degrees, well, the atomic positions in this projection do not change, but since it is a 4 bar symmetry, which is not really, there is no 4-fold axis of symmetry, but there is 4 bar symmetry, something, I mean these bonds keep coming up and going down and so on and so forth, right. So, but there is a 4 bar axis of symmetry, right. And then you can prove to yourself that there is also a mirror plane. If you look at so one of these 1 1 0 planes, you can cut that plane and then see that there is a mirror plane. So essentially, if I go to the structure of this structure parameters, right, I can see that the unit cell, okay, so this is a bad setting because well, so it does not take the complete symmetry. So it takes the, okay, so that does not matter, do not worry about it. But a unit cell, so you have a symmetry which is 4 3 bar m, that is sorry 4 bar 3 m, right. So that is your it is a cubic system with 4 bar 3 m sort of symmetry. So it belongs to this point group, right. So the 4 bar 3 m one, so which is here, draw if I have a pen. So this one, right. So this is my zinc sulphide. Okay. So essentially I took the difference between cristobalite and zinc sulphide is the fundamental unit is still a tetrahedron, right. In case of cristobalite it is SiO4 tetrahedron, in case of zinc sulphide it is ZnS4 tetrahedron, right. But it is the way you arrange these tetrahedra, right, that retains the symmetry of the isolated tetrahedron, which is a 4 bar symmetry, right. In zinc sulphide I am just not disturbing that 4 bar symmetry, I am just laterally arranging them so in a periodic fashion such that I do not disturb the 4 bar symmetry, I just put these tetrahedra nicely next to each other, and then so I am also creating a cubic system. So I have a 3-fold axis of symmetry, 4 3-fold axis of symmetry, right. So that is zinc sulphide. It is a good representation of tetrahedral molecule, which is ZnS4, or tetrahedral entity, it is not really a molecule. It is a good representation of tetrahedral molecule, just so preserving its symmetry when it becomes a solid. Okay. So that is one way of thinking about it. Whereas in cristobalite that is not the case, right. So the tetrahedral molecule SiO4, or the moiety or the entity, tetrahedral entity, that by itself has a 4 bar symmetry. But the way I am arranging this, I am not arranging this tetrahedra in any sort of nice orderly fashion, I am arranging them such that I preserve 3-fold axis of symmetry about the 4 1 1 1s, but I do not, I mean I because of this haphazard alignment I do not get the 4 or I do not preserve the 4 bar symmetry, right. So then that becomes so what I get is a cheap 2-fold axis of symmetry, right. So that is it, it is not more symmetric than 2-fold axis of symmetry, right. So you can actually think of symmetry in this fashion, right. So you can, I mean, so symmetry in a crystal, right. So a crystal can lose a symmetry that an individual molecule has, right. So if you are going from chemistry where you are looking at symmetry of individual molecules to a solid or a crystal, then so you are most likely going to reduce the symmetry from a molecular entity, okay, or preserve exactly that symmetry. You cannot go to a more higher symmetric structure, okay. So that is the point that you might want to take home. Okay, so that is about the cubic crystal systems. 4 3 and then the m should come, that is about the cubic systems. What we missed out are the trigonal systems. the hexagonal and trigonal, where I have three-fold axis of symmetry. So, I can have 3m, 3 bar m, the various point groups. Instead of 3m, I can have 3 2, right, and 3 bar, right. So, these are the various trigonal systems that come up. There can be a 3 by m, but 3 by m also becomes one of these hexagonal point groups. So, I do not use 3 by m, I think we did do that, right. So, 3 by m becomes 6 bar, right. So, if I am going to, if I have a point group which is 3 by m, then so I am going to put my entities which are here, 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 but the entities actually are also getting mirror reflected with respect to this plane, right. So, this plane is my mirror plane. I am just loosely drawing it, right. So, this is my mirror plane, and here is my three-fold axis of symmetry, and there is a mirror, right. So, that is okay. It looks like a nice face, but with a nose in between, that is fine, but the issue is 6 bar actually does exactly the same thing. So, instead of using 3 by m, I am going to call this sort of a symmetry as 6 bar symmetry. It is just one operation, one improper rotation operation. Okay, about that point. So, you would not see point groups such as 3 by m, for example. Okay. So, a hexagonal system for again one can list out all the point groups in a hexagonal system, and these point groups are 6 bar, 6 2 2, 6 by m, 6 by m exists, right, 6 by m m m, 6 bar m 2, and so on and so forth. Now, if I ask the question, how many of these have inversion symmetry, right. So, you can go back, or so I can look at the stereograms. So, let us go to a pen or a laser pointer. Okay. So, for example, I select a trigonal system 3m and I ask you the question, is there inversion symmetry in 3m? So, you can say, you can easily look at this the stereogram, and you can look at the asymmetric units, right. So, in the stereogram, and you can easily say that okay, there is no inversion symmetry. Okay. Whereas, if I am taking something like 6 bar m 2, right. So, there also, if I have a dot here, right. So, I should have a circle here, that so then I say that it has an inversion symmetry, but I have I do not have a circle here, I have both a dot and circle there, but no circle here. So, this is also no inversion symmetry, no 1 bar, right. I am just going to strike it out, no 1 bar here, no 1 bar here, right. So, whereas if I take 6 by m, right. So, something like or 3 bar m, for example, 3 bar m has inversion symmetry. I have this one and this one which are inverting, right. So, this has inversion symmetry. I can just look at 6 bar by 6 by m mm, this is the holohedral group of the hexagonal system. This also has inversion symmetry, 1 bar exists, right. So, you can just see this and tell. Okay. So, for example, you can also look at the same thing in cubic systems. So, even in cubic systems, 4 bar 3m, which is the one that I just spoke about, the zinc sulphide, there is no inversion symmetry in zinc sulphide, right. So, as a result, zinc sulphide turns out to be piezoelectric. We did this earlier, right. So, materials or which do not have inversion symmetry are so the piezoelectric properties are not 0. If a material has inversion symmetry, I do not even need to worry about the third rank tensor, which is the piezoelectric tensor, right. So, so I can just look at these stereograms and identify whether there is inversion symmetry or no inversion symmetry, right, but I have to first draw the stereograms properly. Okay. So, with that, let us end, I mean, so okay, so if I just again go back and then identify the number of I can keep all these annotations, if I go back and identify the total number of, so I have in every crystal system I said that there are so many point groups, I can add up all these point groups and total number of point groups I will have are 32, right. So, these 32 are compatible with improper rotations and proper rotations as operations, right. Improper rotation also includes a mirror, right. So, these are the various operations that we have looked at, mirror, inversion, right. So, 1 bar is inversion, 2 bar is mirror, right. So, I am just going to call them as improper rotations, right. So, 32 point groups, this is not 32, this is 32. 32 point groups include so proper, improper rotations and combinations. So, these are the symmetry operations. Okay. Okay. So, just before I move on from point group, so here in the, again let me repeat it, I sort of said this yesterday. In the trigonal system I have a point group which is 3 2, and by 3 2 I mean that I have a c axis of the hexagonal system in the hexagonal coordinate system, right. So, I have a c axis which is a threefold axis, right. So, I take my coordinate system here such that the basal so I have two A and B are at 120 degrees with respect to each other, and C axis is coming out of plane, right. So, C axis is at 90 degrees to both A and B. Okay. So, that is the coordinate axis that I am considering, and with respect to C axis I have a threefold axis of symmetry, and with respect to one of these B or so B or A axis, because there is threefold symmetry, does not matter which one you take. If there is twofold axis about B, there should be twofold axis about A. Okay. There is twofold axis of symmetry. Okay. So, that is what this means. Now, there is another point group which is 2 3, and it can be easily confused with 3 2, but 2 3 typically so you use it for, so by now so if you have seen these point groups for quite a while, you know that if I am saying 2 3 I am actually looking at a cubic system, right. So, there is nothing just by looking at the notation that tells that this is cubic, this is this is trigonal, but it is just so it is just based on experience. You can not experience, but so looking at it, and then so it is a standard notation that 3 2 will be a rhombohedral or will be a trigonal system, right. So, with only one threefold axis of symmetry, whereas 2 3 is going to be a cubic system with 4 threefold axis of symmetry, right. So, the 3 2 3 means I have 3 twofold axis of symmetry and 4 threefold axis of symmetry. So, this is just the notation, one needs to get used to it, right. So, it is so what is the logic, why can't I use 2 3 here, 3 2 there, all these things, so we do not ask these questions because it is just a notation, it has been followed by crystallographers for time immemorial. So, we just accept it. Okay. So, now here the 32 is not any point group, it is not 3 2 or something, this is 32. Right. So, this is the number 32, and so these are the total number of point group that you can find in crystals, right. So, these are crystals, which means that is compatible, all these point groups are compatible with translational symmetry. Okay. So, where is the translational symmetry coming? I have not put in any translational symmetry. The reason that I am just considering rotations and proper and improper rotations which are 1-fold, 2-fold, 3-fold, 4-fold and 6-fold only and nothing else tells me that these are the rotations which are compatible with translational symmetry. So, that is where the translational symmetry aspect is coming in. Okay. So, just keep all these facts in mind, and everything becomes smooth sailing from then on. All right. So, with that, let us now do some other exercise, which is okay. So, I have 32 point groups, and I am interested in asking the question, how many of these are non-centrosymmetric. Okay. That is easy to answer. So we can always count, we can look at the stereograms and then do a counting and say, okay, all these point groups are non-centrosymmetric, all these point groups are centrosymmetric. Okay. So, in fact, it has been done for you, right. So, in this slide I am actually telling you which ones are so all the red ones, all the red point groups are centrosymmetric point groups. For example, 1 bar, yeah, 1 bar is inversion. I mean, so so by definition 1 bar is inversion. So, the operation 1 bar is inversion. So, of course, so any centrosymmetric point group should have 1 bar in it, and 1 bar has 1 bar in it, right. So, I am just stating something very trivial. 2 by m, I said you take any axis, any rotation axis, and then cut it with a mirror plane. You are making a point, right. So, wherever this mirror plane cuts the two-fold axis, there is a special point there, and that point will have inversion symmetry, that you can prove. So, 2 by m, 4 by m, 6 by m, right, and MMM is actually 2 by m, 2 by m, 2 by m, right. So, in the longer notation, so there is a 2 by m here, so that has that is centrosymmetric. Then 4 by m mm, right, so that is centrosymmetric. Then 3 bar itself is a centrosymmetric point group if you think about the stereogram, right. So, I have one triangle on the top and the other triangle which is chirally inverted on the bottom, right. So, the octahedral void is a 3 bar is a point about which there is 3 bar symmetry, right. So, 3 bar itself has centrosymmetric, and then you are additionally adding a mirror plane. So, the centrosymmetry remains, so and so on and so forth. So, 3 bar. Then in cubic systems, not all cubic systems are centrosymmetric, right. The only cubic systems that are centrosymmetric are M 3 bar M. So, all your FCC metals typically have centrosymmetry, imagining that these are metals like platinum, gold, which crystallize in FM 3 bar M, right. So, the M 3 bar M is the underlying point group, then that will have centrosymmetry, right. So, M 3 bar, right, so that also has centrosymmetry, and then 6 bar, so you can only 11 point groups have centrosymmetry, right. So, the rest all are non-centrosymmetric point groups, right. So, if I have to look for my piezoelectric materials in among a class of so I have classified all my crystals, right. So, into 32 different point groups, right. So, all my crystals will have some sort of underlying point group, and all these crystals can be classified into 32 different point groups. Then I give you a crystal and I ask you, I want to actually check if this is piezoelectric or not, and piezoelectric tensor is a third rank tensor, that we know, it is Dijk, right. So, we have done this earlier, and so if I ask you the question, is Dijk so would the crystal that I give you have a Dijk that I can measure, right. So, that is the question that I ask. Then you can just ask me, or you can actually do some X-ray diffraction and try to find out what is the underlying point group, right. Now, if the underlying point group turns out to be one of these centrosymmetric 11 centrosymmetric point groups, then I say, all right, you are looking for something which is not reasonable, right. So, crystallography prevents it from being piezoelectric. So, please take your crystal and go away, this cannot be piezoelectric. So, that is a very fair answer, right. So, if I have to look for piezoelectric materials, I will look among the 20 non-centrosymmetric point groups, actually 21, right. Right. So, if I have materials which belong to one of these 21 non-centrosymmetric point groups, I will suspect that there is piezoelectricity there. I should still measure it, that is a different problem, right, but I will suspect that there is piezoelectricity, and then I will just select that. If it belongs to one of these other 11 point groups, right. So, if the underlying point group belongs to the other 11 point groups, then I will just throw that material away. I am going to not measure anything, I am going to just say that symmetry forbids it. Symmetry is a very strong argument. Symmetry can forbid things from happening, right. Symmetry can say this cannot be piezoelectric. If you are confident about your symmetry determination, this material cannot be piezoelectric, right. So, if it belongs to one of these 11 point groups, okay. Now, it also turns out, we will prove that later, that there is another non-centrosymmetric point group which is 432, it is a cubic group, but if you calculate the piezoelectric tensor of 432, coincidentally the piezoelectric tensor becomes 0 by virtue of having 4, 3 and 2, right. So, it is nothing to do with centrosymmetry, but just coincidentally all these symmetry elements in combination make the piezoelectric tensor 0, right. So, that is an it is an addition. So, you should not have centrosymmetry, if you have centrosymmetry or your point group is 432, then my material cannot be piezoelectric, or my third rank tensors do not exist. It is not just about piezoelectricity, even my second harmonic generation tensor, right. So, chi ijk or d ijk, they are all 0 for these 11 centrosymmetric point groups and an additional point group which is 432. So, for 432 it just coincidentally becomes 0. Okay. All right. So, okay. Then comes the idea of what is a polar group. Okay. So, maybe we will stop this lecture here, and maybe in the next class we will start by looking at so far we have classified all the point groups. We said point groups are very important. The properties of crystals actually depend on point groups, right. So, we have classified them based on say several crystal systems. We said 21 of them are non-centrosymmetric. So, if you are interested in something like piezoelectricity, second harmonic generation, the third rank tensors or odd rank tensor properties, first rank, third rank, fifth rank and so on and so forth. Well, all these materials that belong to these 11 point groups, right, and for a third rank tensor a 432, right. So, we do not look at these crystals, we just look at all the other crystals, right. So, to measure these properties. Okay. So, in the next class we will actually look at what what polar point groups are essentially, and polar point groups are very crucial to understand whether material has some what is called polarization, the so called ferroelectric materials, right. So, we will spend some time in trying to understand what this is. Okay. So, we will start there and then proceed towards space groups. Okay. So, I will see you in the next class.